Hello, last section of chapter 4. It's a short section. It's called differentials. And what we are going to do here is to try to find tangent line approximations, which is a strategy that can be used often in real-life situations to find an approximation of the real value of a function. In particular, it happens in real life if you don't have a function at all. Sometimes functions can be pretty hard to find. So the idea is that if you have a function like this, and we will pretend now that we don't know what this is. It's f of x equals something, but we don't know what. What we do know is one point on this graph, and we also know the slope at this point, which, if you think of real life, is quite reasonable. If you're on a road that goes up, let's pretend this is a road, and so the car would go up, up, and then the car would go down here. You're not going to find a function for what the road is. However, you may be able easily to find the altitude where you are, and you might, with simple tools, be able to find the slope of the road exactly where you are. So finding a point and the slope is easier than finding the entire function. Then, with that, you are able to make an approximation of the altitude of the road a bit further. So here, the road is actually at this height, but with our approximation, we will estimate that it is up here. So not too bad, not too far away. How do we do that? Because we have a point and the slope, which are typically easy to find, or in math exercises they would be given, we can find the equation of the tangent line, and then instead of finding the point that is really on the road, so the real output, we calculate what the point is going to be on the tangent line. So this works at one condition. It works for points that are not too far away. This point and that point are not too far away. They are not too distant from the original point we're using, and so the output would not be too bad. But imagine if we looked at a value here, then the road is at this height, our tangent line would be way up here, so the quality of our approximation would be very poor. We use these tangent line approximations for outputs that are very close, in fact much closer than this ideally. If you look very close to our original point, the road and the tangent line are almost overlapping here, and here they're pretty much overlapping. Okay, so let's see an example. Find the tangent line approximation of f of x equals sine x at the point where x equals pi over 6. That is really just finding the tangent line. But we are using it for x equals pi over 6. And then in part B and C, we will use our tangent line to find an approximate value. So we need a point. It's the point pi over 6, 1/2, because sine of pi over 6 is 1/2. And we need the slope, so we'll take the derivative. F prime of x is cosine x. Therefore, f prime of pi over 6 is √3 over 2. That means the tangent line at that point is y minus 1/2 equals √3 over 2 times x minus pi over 6. This is something we started doing in section 3.1. Now we are going to use it to find the approximate value of f of x equals sine x at x equals 0.5. This is not part of a triangle. We know sine of 0.5. Nobody among us knows the value, but notice that I chose the value that is very close to pi over 6. In fact, I have my calculator with me right here. Pi over 6 is 0.524. So the graph of sine x and the graph of the tangent line are going to be almost the same, because I'm looking at a point that is super close. 0.5 is super close to 0.524. So I can plug x equals 0.5 in my tangent line, and I get, using the calculator, 0.4795628. Now what is the real value of sine of 0.5? You can plug it in your calculator, of course, and you get 0.4794255. So you see there's 3 decimals that are the same, using a tangent line rather than the sine curve. Here's another example. Use a tangent line approximation at x equals 3 to approximate the output of f of x equals x squared at x equals 3.1. So again, we are using x equals 3 to build a tangent line, and then we will look at the value of y on my tangent line for x equals 3.1. And it should not be very far from the y value on the function itself, because 3.1 is so close to 3. I know we can calculate 3.1 squared. In fact, we will do it. The value is 9.61. That's the real value on the parabola when x equals 3.1. But how good is the tangent line approximation? Well, x equals 3, so the point on the parabola is the point 3,9, and the slope at x equals 3 is 6. I found that using the derivative f prime of x equals 2x and plugging x equals 3. So my tangent line is y minus 9 equals 6 times x minus 3. And if I plug in 3.1 for the tangent line, I get y equals 9.6. So the real value is 9.61. I found 9.6. Not too bad. A classic question in AP Calculus AB is to ask whether our result is an overestimate or an underestimate. And they will ask to justify using calculus. So this classic question will come in situations where we are not able to compare with the real answer. Here we were able to find that the real answer is 9.61, but we won't be able to do that always. So ours is an underestimate, right? We got 9.6 instead of 9.61. So how do we do that? The trick is to think of concavity. We have a tangent line. This is the tangent line that we found in this problem. And because we know the function itself is concave up, which we will calculate later, we know that the function is going to be above the tangent line. I have a tangent line, and above it is a concave up function. If the function was concave down, then it would have to be below the tangent line. So how do we check that the function is concave up? We need to find the second derivative. F prime of x was 2x, therefore f double prime of x is equal to 2, which is positive, and so that means the function, the parabola, is concave up. We know that. F of x equals x squared. We can see it in our head. It's a concave up function throughout. So when we have a concave up function, it means it lies above its tangent line, and so our estimate, which was on the tangent line, is an underestimate. The function is over it, so our approximation is an underestimate. This word is a bit confusing here. So that's it. Thank you.